समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. So very good morning to everybody. Are you able to hear me?
Yes, sir.
Okay. Guess now you're able to see my slide as well.
Yes, sir.
Is the video fine?
Yes, sir.
Okay. So let's get going from where we left off last time. We were in the process of identifying certain variables associated with structural analysis in general and flight vehicle structures in particular. And these include basically the state variables, certain constants associated with the problem, and maybe the equations which relate these variables and constants. We just wanted to put together all the concepts and variables, constants, equations that you have come across in various structures related courses like strength of materials, elasticity, etc. And then see where each of these terms stands in the bigger perspective, because as flight vehicle people, as aerospace engineers, if we don't see a bird's eye view, who else will? So the idea is to understand the bigger picture so that when we go into the details of each one of these analyses, the actual equations, the derivations, etc., things are much more clearer. So that's the whole purpose of this particular exercise that we had started out with. So the question that I had asked is which variables describe the state of a mechanically loaded structure, and that's what we'll continue to look at. I'll bring back the blackboard that we were using. I just changed the color codes of whatever we had written. These were all based on inputs that you had provided in the previous class. So now let's continue. I had a few more inputs before we arrive at certain broad inferences from what we have put together over here. So I'd like you to continue giving your inputs in terms of various variables that you have come across in various problems, in various textbooks, in various lectures, various constants that you have come across, various equations that you have come across in order to analyze structures in general. So please go ahead. Any other variables, that constants or equations that you're familiar with in structural analysis or strength of materials? You can unmute yourself and let me know. Fatigue, okay.
Joint efficiency.
Okay. Okay, we wrote certain things related to the joint properties, so I'll leave that aside. What else? Yeah, come on. Think of all kinds of problems that you have encountered in your exams, in your homeworks, in your GATE exam, for example. Many of you have written that. So just think of various variables that you have encountered in strength of materials or structures. various constants. We listed out a few, for example, in the last class, like the stiffnesses of the material, bulk modulus, Poisson's ratio, shear moduli. What else?
Mean compliance.
Come again?
Mean compliance.
Okay. We put compliance over here. Okay. What else?
Sir, stress intensity factor, shear length factor.
Okay. What is the second one you mentioned?
Sir, shear length factor and stress intensity
Okay.
factor. Sir, flutter.
Okay. Okay. Anything else? I mean, how much ever we list for however long, this would not be a comprehensive list. There'll be many that we leave out. But I want to at least populate it to some extent before we go for inferences. Yes, somebody had something to say?
Creep loading.
Creep loading, okay.
Energy release rate.
What load?
So, energy release rate. ERR.
Okay.
Fracture mechanics.
Okay. What we typically abbreviate as SERR or strain energy release rate. Okay.
Yes, sir.
Next. Yeah, come on.
Strain rate based loading systems.
Okay. So load as a function of the strain rate. Yes.
Thermal stress.
What stress?
Thermal stress.
Okay.
And strain. Thermal strain. Volume fraction.
Okay. Okay.
One versus stress.
Okay. Then
So slender ratio
slenderness ratio, good.
and the radius of gyration.
Okay, very good. Some more.
So flexural rigidity.
Okay. Next. Related, other than flexural rigidity, what other rigidities that are you aware of?
So torsional rigidity.
Okay.
Any stress function, torsional stress function,
Okay.
tangent stress function. Sorry.
What's the third one you mentioned? Area and Prandtl, other than that?
No, sir. No, sir. The Prandtl one I mentioned it as
Okay. Yeah. Okay. Yes, what else?
Since there is flutter, we can keep velocity of flow around the body.
Okay. Yes.
Certain damage tolerance.
Okay. Okay.
Vector of safety.
Yeah, I think we wrote that earlier.
Impact load.
Mm-hmm. Yes. What else?
Eccentricity of loads.
Eccentricity of loads, very good. Okay. Okay, what about the equations? So we mentioned certain topics, but what about the equations that you are aware of which help to relate between these variables and constants and therefore lead to determining certain unknowns in terms of certain known quantities? What all equations are you aware of in strength of materials and elasticity?
Equilibrium.
Okay.
Boundary conditions.
Okay, yeah, I think we mentioned that last time.
Strain compatibility.
Okay, very good. Strain compatibility. Okay.
Continuity equation. Continuity equation.
Continuity equation. Okay. What continuity in what?
The continuity in mass.
Okay. Because in fluid mechanics, continuity automatically means mass conservation, but here continuity can mean various things in structural mechanics. So that's correct. Continuity equation in terms of the conservation of mass. Yes.
So conservation of angular momentum balance. Linear
Okay.
momentum balance.
Very good. Okay, so another way of saying the equilibrium equations, but that's where it comes from. Yes, the principle behind it is conserving the angular and translational momentum. Yes. What other equations?
Rule of mixtures.
Okay. So in fact, we looked at it while we looked at the micromechanics in this course itself a few weeks ago. Yes, what else?
Constitutive equations.
Okay.
Support circle.
Okay, very good. Okay. Hooke's law, okay.
Compatibility equations. Okay, we wrote that.
Yeah.
Deflection equation, sir.
What the deflection equation means?
So bending deflection equation.
Bending
That is-
deflection equation, okay. Okay.
Merchant circle.
What circle?
Merchant circle, sir.
I'm not aware of that. What is this?
Sir, it is used to calculate like cutting velocity, that kind of thing, sir. It is related to manufacturing, sir.
I see. Okay. Nice. Interesting. How do you spell that?
Sir, merchant circle.
Okay.
Sir, MERCHANT.
Okay. Good. I learned something new today. Thanks.
Sir, tool-like equation, sir. VT power n equals to constant.
Okay. What's that? Tool?
Sir, tool-like equation.
Tool length.
Life, sir.
Life. Okay. Okay.
Sir, SN curve.
SN curve. Very good.
Bernoulli-Euler equation.
Euler-Bernoulli equation. Okay. So I think we wrote something related to that. So we'll leave it at that.
Shear flow equation.
Shear flow.
And flexural shear.
Okay. Very good.
BMSF diagram.
Okay.
Sir, homogenization equations which we use in composites.
Homogenization. Okay.
Failure and Miller. Failure and Miller.
Failure enough. Very good. Okay. Any other concepts? Equations, variables, constants. Okay, I guess you've exhausted most of what you know. So let's now try to understand why we wrote this in this particular way. We just wanted to see where each one of these concepts, variables, etc. fit in. So that was the whole purpose of this exercise. So the question that I had asked was which are the variables which describe the state of a mechanically loaded structure. The load can come from various sources. So you mentioned different kinds of loads. You mentioned how the structure behaves through various concepts, through various variables, through various constants associated with the material, etc. And how it responds in terms of its deformation, etc. So you mentioned various variables associated with that. Along with this, we've also been trying to look at the other question. Are we able to kind of classify these variables that we have listed into 4 general categories or sets? So that was a hidden question which I had not stated to you, but I was kind of inherently doing that when I was putting these variables in a set of columns. But as you might have noticed, it was not just 4 columns, it was more than 4 columns. So what are the additional columns that are associated with these? So it's not just the 4 general categories or sets that I'm talking about over here, but we're also going one step ahead and looking at what are the three sets of equations which relate these four sets of variables. So a classical kind of problem will be one set of these variables are given, the other three sets are to be determined using the three sets of equations. So right now everything might seem a little hazy, but once we give names to these four sets of variables and the three sets of equations, things will become a little clearer. So let's go back to our columns over here. So if you can look at, there is a little bit of haziness. Some of these variables which I've listed in certain columns can perhaps go into multiple columns. Like for example, boundary conditions I already mentioned could be of two kinds. That is the boundary conditions associated with the displacement or rotations on the one hand, and the boundary conditions which are associated with the forces or moments on the other hand, whether it's concentrated or distributed. So all of those mean that certain things could be force boundary conditions, certain things could be geometric boundary conditions, etc. And so some of these might figure in multiple columns. But essentially, if you look at it, these are alternate columns where the odd numbered columns 1, 3, 5 and 7 are all associated with the sets of variables that we want to identify or constants that we want to identify. And then the even numbered columns, second, fourth and sixth over here, are the ones which are the equations which help us to relate these quantities, some of which might be known to us, some of which can be measured, some of which can be estimated, and then the others which are unknown need to be determined using these equations. So let's see first of all what are those four general categories of variables that we have identified over here. So let me use probably a different color with that. Yes, I am. Oh, are you not seeing that? Okay, just let me see. Oops. So here.
So actually I was able to see.
Okay, so anyway, so I just stopped sharing and started resharing. Yeah, okay, good. Welcome. So now, so what are these four sets of variables? We mentioned specific variables and constants, but now can we classify them into four broad categories? Some, as I said, like boundary conditions might go in multiple columns, but those are equations. But now we're talking of the variables or constants, which can be classified into four sets. So what are those? If you look at the first column, you can talk of them as, in a generalized sense, as loads. Okay. Then the third column are basically the stresses. And then the fifth column are basically the strains. And the last one are the deflections, or deformation if you want to call it. Okay. So now these are the four broad categories that we have. The first set is the set of load variables. Second is a set of stress variables. The third is a set of strain variables. And the fourth is a set of deflection or deformation variables. Okay, includes rotation, etc. Some of which we didn't mention, but okay. So these are in a generalized sense. Now we are using these concepts. Now, if you look at it in reality, what we are actually observing is that we apply a certain set of loads and are able to visually or using certain measuring techniques, able to see what is the kind of deformation which is happening. So what is actually experienced by an observer, either a human or through an equipment, either through our naked eyes or through certain equipment, are basically these loads and deflections. Either you apply a certain set of specified loads on a structure and observe the kind of deformations or displacements, rotations that are happening to it, or you apply a certain desired deformation in terms of displacements and rotations, and estimate the kind of load that is required in order to accomplish that kind of a deformation. So these last set of columns, that is the loads over here and the deflections that you have over here, are the ones that are directly applied and or observed, and these are the things that we actually want to relate. But if you look at it, for most problems, the relationship between the load and the deflection, which is what we eventually want to have, is a little more complicated. So in order to make these a step-by-step approach to enable a better understanding of what is happening in this cos being the load and the effect being the deflection, between this cos and the effect, what is actually happening in between, what is the chain of events, or what is the logic behind that. In order for that, we are introducing these two imaginary kind of quantities, the stresses and the strains. Imaginary in the sense that you're not actually applying a stress or a strain or measuring a stress or a strain directly, even in a strain gauge for that matter. So what you're actually looking at is the deflection that is happening, which is in turn looked at from a strain gauge perspective. And similarly in a load cell or whatever, it is a load that is applied, which can then per unit area come up with either a nominal stress or the true stress, etc., depending upon how you actually calculate it. So these two concepts of stress and strain are not directly observable or applicable. It's just that, for example, pressure is a load that you are applying, but that pressure causes a stress as a reaction or a response of the structural material, and that's happening at each and every point within the structure. And in order to understand the logic of flow from the load, which is the cos, to the deflection or deformation, which is the effect, we are introducing these two concepts in between, so that the relation between these in a consequent way is much simpler, rather than directly relating the load to the displacement, which we eventually will do, which is what we want to achieve, but we want to do it in a step-by-step approach. So that's where these equations come into picture. So the equation that we have between the load and the stress, and by this we mean not just what exactly load means or what it means, but in a much more generalized sense, which is what we are trying to do over here. We are now introducing these equations between these quantities. So the first set is between the generalized loads and the generalized stresses, which we call as the equilibrium equations, under which all of these other things that we listed out come out as examples of that. So the equilibrium equations are basically things that are relating the loads and the stresses using certain laws of physics, which are basically natural laws, which also, as some of you pointed out, involved certain balance or conservation of either the mass and momentum, energy, etc. Some of these things are coming into picture over there, basic laws of physics, in order to relate these stresses to the loads. But predominantly it's the conservation of the translational momentum and the conservation of the angular momentum, which are resulting in these equilibrium equations relating the loads to the stresses. Now similarly, if you relate the stresses to the strains, which is the next step, so you're going in step by step, instead of jumping from the load directly to the displacement, instead of that you're going in step by step by introducing these concepts of stresses and strains. So once you have introduced stress, you're relating the load to the stress by using the equilibrium equations. The next step is to relate the stress to the strain, these two fictitious quantities that we have kind of introduced, and this is basically what is your constitutive equation. So the constitutive equations, which is an example of which we saw when we introduced the various assumptions, 10 in particular, associated with composites, but which can be specialized to metals and other materials as well. Those are the constitutive equations. So those involved, for example, the Hooke's law, etc. So those are the constitutive equations. And then we have to finally relate the strain to the deflection, what we call as the kinematic equations. So now we have three sets of equations: the equilibrium equations, the constitutive equations, and the kinematic equations, within which there can be many types, which is what examples of which is what we listed out based on the inputs that you had given me in terms of various variables, equations, etc. that you knew. So these three equations, sets of equations rather, help us to determine the unknown quantities in terms of the known quantities. So that is the overall picture. Now we will see, as I said, equilibrium equations depend on the physics and therefore the laws of nature. Similarly, if you look at the constitutive equations, they depend on the material alone. So it's, for example, many of the things that we listed, for example, like the Young's modulus or the bulk modulus, Poisson's ratio, shear modulus, the fracture toughness, etc. Many of these properties are basically properties which are associated with the particular material that we are using or set of materials that we are using. So whereas the equilibrium equations depend on the physics of the problem or natural laws, the constitutive equations on the other hand depend entirely on the material or material choices that you're making, a set of materials that you're distributing in a certain way. On the other hand, the kinematic equations depend entirely on the geometry. So that's not just the geometry of the original structure, but what happens to that structure as it is deforming, how its geometry is changing in terms of the sizes changing, the shape changing, a combination of those two changing to result in various kinds of deformation. So that's basically what your strain displacement relationship is an example of. So all of that comes under kinematics, and right now we are not even restricting this whole thing to static problems. For example, we listed out various examples that you mentioned of loads which are like flutter, for example, or impact, for example. Some of you mentioned fatigue. So these kinds of loads are time dependent loads. So we are allowing for those dynamic loads as well in this whole exercise, and we are saying whether it is a statics problem or a dynamics problem. And in a dynamics problem, whether it's a vibration kind of a problem, or it could be a fatigue kind of a problem, it could be an impact kind of a problem, or an instability associated with the with either the geometry itself in terms of a buckling, like an elastic instability, or it could be an aeroelastic instability like flutter, as one of you gave an example of. So whatever it is, that flutter is actually getting loads from the aerodynamics. So that's basically why I listed it under loads, that the aerodynamics is providing the load, and that load is resulting in certain ways in which it is combining with the geometry, with the material and its behavior, so that eventually what is happening is an instability in the aeroelastic behavior is occurring, and an example of that is flutter, a dynamic instability. Whereas you could also have something called a divergence, which is a static aeroelastic instability. We'll touch upon these things in a later class. But here we have a kind of a big picture where we have categorized all these variables into 4 categories, and then we have tried to relate them through these sets of equations, and then see how this connectivity can help. Now we will get on to certain actual examples of this set of these variables and these equations in terms of quantities that you are already familiar with. We will start by looking at isotropic materials being used to make, let's say, beams, to make axial rods, to make shafts. Yeah, somebody had a question?
Sir, are you sharing the slides? Because I'm not able to see.
Is anybody else able to see it?
Yes, sir, it is visible like this.
Okay.
We can see. Blackboard is visible.
Okay. I think if you might have pinned my video or something, so you can just unpin that and pin into your the slides, so that you can also see it just like the others.
Okay, sir, I will try it.
Okay. Sometimes what happens is automatically it keeps changing between the various input sources that it has. That's what Teams does. So if you want to stay fixed on something, you can actually pin that so that it doesn't get changed. Okay. Right. So what we will do is, now that we have understood these four general categories of variables or constants and three general categories of equations relating them, we will look at specific examples associated with rods to start with. Then we will go on to shafts, and then finally to beams, and then we will see, based on these concepts, how they are kind of related. Because the reason why I want to start with these four simple examples, 3 or 4 simple examples, is that you are familiar with the end result of these already. So that way you'll understand the concept much better, and then when we go to more complicated materials like composites and or more complicated loading situations or combined loading situations or plate-like structures, shell-like structures instead of beams, you'll be able to understand the whole thing from the same perspective. So that is the whole idea. So it's very important for you to not only understand these four categories of the variables and 3 categories of equations, but what these 3 categories of equations depend upon. Equilibrium equations depend upon the physics of the problem or the natural laws. The constitutive equations depend upon the choice of materials that you have, and eventually the kinematics depends upon the geometry that is involved. And of course, in a dynamic problem, the geometry is changing with time, and that dynamic geometry is what we are talking about. So are there any doubts on this before we get back to the slides? Okay, so let's go back to our slides. So we have been able to answer these questions. What are the 3 sets of equations relating the 4 sets of state variables? The 4 sets of state variables are the load, the stress, the strain, and the displacement, and the 3 sets of equations are the equilibrium equations, the constitutive equations, and the kinematic equations. Just, you're not able to see my slide, are you? Why that happens? So let's kind of summarize what we have just stated in words and also on the blackboard. There are 4 important quantities which are used to describe the mechanical state of a structure. They are loads, stresses, strains, and deformation. And now there are equations relating these 4 quantities. So there are 3 sets of equations, and because you assume that certain data is known to you, and based on that known data you're determining the other 3 sets. But not all problems would be in such a categorized fashion. You might know a few loads, you may not know certain loads, you may know a few deformations, you may not know a certain set of deformations. So it might be a combinations that you could have, but nonetheless there are 3 sets of equations which are represented by these double-sided arrows in this particular slide. The green arrow being the equilibrium equations, the red arrow being your constitutive law or constitutive equations, and the yellow arrow being the kinematics or the strain displacement relationships. Okay, so this is what we have as these 3 sets of equations. And then associated with that are the boundary conditions. Some of you gave that as an example as well, which is very good. So associated with the equilibrium equations are what are known as the natural boundary conditions, or basically boundary conditions which are known in terms of loads, which could be either concentrated loads or distributed loads. Concentrated loads like for example where the control surfaces or engines are attached. In essence, actually they are also distributed loads because it's not attached at a point, it's over a finite area that these attachments actually take place. So most loads are actually distributed loads, but the natural boundary conditions basically give you those loads at different locations on the surface of a structure. For example, on an aircraft wing, the pressure distribution that is coming from the airflow, the shear distribution that is coming because of the viscous nature of the flow, and the boundary layers that are involved, the concentrated or relatively speaking concentrated but also distributed loads coming from the weight of the engine, etc. Then the body forces that are there, those are things that are there in the loads. But the natural boundary conditions are basically those which are in terms of forces. There can be some in terms of moments as well. There could be a torque which could be applied, for example, at the end of a drive shaft. So that torque could become the boundary condition at one end of that drive shaft. Similarly, as far as the kinematic equations are concerned, they are supplemented with what are known as the geometric boundary conditions, where, for example, you specify the displacement or rotation at a particular point. So, for example, where the wing is attached to the fuselage, we assume it's almost a fixed boundary condition, which means that relative to the fuselage, the root of the wing is going to have zero displacement and is going to have zero rotation approximately, or in more so in reality it is negligible deflection or rotation compared to that location of the fuselage to which the wing is attached. So it's basically a fixed boundary condition that is over there. On the other hand, if you have a simply supported boundary condition, you know that it's a mixed kind of a boundary condition, where one of the boundary conditions states that the displacement is zero, which is an example of a geometric boundary condition at a hinge. On the other hand, at the same hinge, we know that there can be no moments because it allows the rotation to happen freely, which means that you're basically allowing for the moment to be zero. So that means you're specifying the moment, and therefore it's a natural boundary condition. So the natural boundary condition need not necessarily be a finite non-zero value of the load which is specified, but also telling that that load is zero at a particular location is also a form of saying the natural boundary condition itself. On the other hand, if it's a free end, like the tip of the wing or the tip of the horizontal tail or the tip of the vertical tail of an aircraft, you would see that it's a free end. In other words, there's no load that is applied over there. A concentrated load is not applied over there. So basically what you're saying is that the shear force or the bending moment is equal to zero at that particular point, which is again a natural boundary condition. So it would come under this green set of equations, which are broadly clubbed as the equilibrium equations. So essentially what we are ending up with is with a boundary value problem, wherein we have a set of differential equations. Sometimes, depending upon how the problem is formulated, it could be integral differential equations. Sometimes algebraic equations come into picture as well. For example, the Constitutive Law is a set of linear algebraic equations, which is basically a stress strain matrix, which is nothing but your Constitutive Law, or using a matrix which is either the compliance, which we also call as the flexibility matrix, or the inverse of that, which is the stiffness matrix or rigidity matrix. So that is basically what the set of equations would be. Some have a nature of differential equations like the strain displacement or the equilibrium equations in general, the 3D equilibrium equations, but some would have the form of algebraic equations like the Constitutive Law, and if you involve the strain energy and some kind of a variational principle to derive it, some of the equations equations can be integral in nature. So in general, you would have a set of integro-differential algebraic equations which are coupled. May not be all the variables are coupled with each other, but there is definitely certain level of coupling, and then you're given certain data in terms of either quantities which are desirable or quantities which are measured and therefore known, and in terms of these you are trying to get the other quantity. So that is the whole story behind this. So let's also look at what these equations depend upon, which we already mentioned in the blackboard, but it's very important to understand that this dependence is pure, and therefore any changes that you make, you will know which area or which set of equations needs to be changed. So others can be retained. For example, if you are changing, let us say, the geometry alone, you don't need to change the constitutive law, you don't need to change the equilibrium equations, you only need to change the kinematics. Similarly, if you're working in an imaginary universe where the different set of conservation laws apply over there, the only thing that needs to be changed over there are the equilibrium equations. The constitutive law, if it's the same material, the geometry, if it's the same geometry, the kinematics remains the same. On the other hand, if you're changing a material for the same geometry, for the same in the same place you're working, which the same set of natural laws are applicable, therefore only the constitutive law needs to get changed. So this is a very important understanding that what these things are based purely on. So let's repeat that, even though it means more time, it's important because these are very, very critical conclusions that are rather inferences that we are drawing, and these inferences will go a long way in understanding in a very, very fundamental way whatever we eventually plan to do, and will put things in their own places rather than looking at it as entirely new topics, because everything else that we are going to cover will be actually kind of examples of this rather than entirely new topics, so to speak. So the rest of the course will all be to see how various examples of these can be analyzed. So the equilibrium equations and natural boundary conditions are based purely on the conservation laws. On the other hand, you have the constitutive law, which is based entirely on the material, and finally the kinematics and the geometric boundary conditions are based entirely on the geometry that is involved. Both the undeformed geometry as well as the deformed geometry both go into picture in understanding this. So next, if you look at the difference between composites that might be new to many of you and the classical traditional materials like metals that many of you are already familiar with, then the only thing that we need to change is what depends on the material, and what depends on the material is basically the constitutive law. The constitutive law is the only thing, as we said, which depends on the material, and therefore in order to understand composites, we do not need to change the equilibrium equations, natural boundary conditions, the kinematics and geometric boundary conditions, which are all dependent only on the conservation laws and geometry, and therefore do not change when you are moving away from metals towards composites. So then, why there is a difference in the constitutive law of composites compared to that of metals, on the other hand, or let's say metals, polymers and ceramics, all each of them individually, on the other hand, which are the traditional materials which are used. Now combinations of those are being used in a composite, and there are two main reasons why. One is because it's a combination, therefore you have material changing from one place to another, but that is the case even with let's say a bimetallic strip. When you have two metals, let's say aluminum and steel strips joined to each other, bonded to each other, then you're going to have some kind of a composite behavior because of the non-homogeneity, or what we call as heterogeneity, which is basically going from one point to another within the structure. There is a possibility of a change in material, and therefore a change in material properties, which we are broadly putting it as a constitutive law. So that constitutive law changes from point to point, which is what heterogeneity brings in, and that's what the composite actually is one of the complications associated with the composite. When you're moving from one point in a composite to another, you might be moving from one layer of the composite to another layer, where the angles of the fibers might be quite different, or an entirely different set of fibers might be there. Within a single layer itself, when you're moving from one point to another point, you might be moving from a point at which it's a matrix to another point which is fiber, and therefore the properties are going to be different. The constitutive law at each one of those locations is going to be different. So one of the complications that is arising moving from conventional materials to composites is the heterogeneity. The other is the anisotropy, that is, you're now having properties which are going to be different in different directions. So that's basically these are the two features of composite materials that we have to be aware of. Once we take care of these two, then analyzing a composite structure or a metallic structure is very similar to each other, except for going very close to failure and understanding those mechanisms, etc. Again, some certain other differences will creep in, but nonetheless, when you're dealing with healthy structures, which is what we are dealing with most of the time, then the only two problems that we need to worry about moving from a conventional or traditional material to a composite is non-homogeneity, or what we call as heterogeneity, and anisotropy. So there should be ways of overcoming this. We have already seen certain examples of how we can actually do that. Let's take that in a little more formal sense now. So, but what these are, as I already mentioned, heterogeneity means that the properties are varying from point to point, whereas anisotropy means that the properties at a point are varying from one direction to another. So it's different along the fiber direction, different along the direction perpendicular to it, but fortunately, at least in the plane perpendicular to the fiber, there is an anisotropy that is involved over there. So, but nonetheless, there is a change in the property going from direction to direction at a given point. So how do we account for these two differences of composites with respect to conventional materials? So the way we do it is by introducing two concepts, some of which you're already familiar with, either from the past or from this course itself. One is basically, as far as heterogeneity is concerned, we introduce the concept of volume average stresses and strains. In other words, we take a small volume, which is what we call as a representative volume element of that material, which the composite is, which is what the micromechanics that we dealt with earlier tended to bring in. And at the, in that representative volume element, we know that there is a fiber, there is a matrix, and the stresses in the fiber are going to be different from the stresses in the matrix. But if we integrate all of those stresses, each one of the stress components, over that entire volume of the representative volume element, and divide by the volume of that representative volume element, you get a volume average stress. Similarly, a volume average strain tensor as well. And then we of course, in reality, you should have a limit as that volume tends to zero, but you cannot do that, because when your volume tends to zero, you either end up in the fiber or in the matrix, in the real material. That's why we introduced the concept of the equivalent homogenized material, as you might remember. Equivalent homogenized material that we introduced in the case of the micromechanics, to say that we are introducing a fictitious material whose behavior, overall behavior, is similar to that of the actual composite, but what happens into individual fibers and matrix, we need to recover by going to what are known as the recovery relationship. On the other hand, in the case of the moduli, the way we took care of that was by introducing your constants, which are like Eij, Gij, nu ij, etc. These Poisson's ratios, Young's modulus, shear moduli, and also the strengths in those respective directions being specified. So in other words, we are not having a single E, single G, or single nu and single strength associated with each one of these, like the tension, compression, shear, etc., but also tension, compression, or shear in particular directions. That direction is now introduced through these direction dependent moduli like Eij, Gij, nu ij, etc., which in turn affect the constitutive law in terms of which quantities are non-zero and which of those non-zero quantities are independent, and which are what kind of experiments need to be performed to determine them, because the constitutive law, being a material property, is more often than not determined using tests, standardized tests like the ASTM standards are used to design certain specimens and arrive at certain repeatability for over a certain range of specimens, and then you from those stress strain curves that you have, you arrive at the slopes, etc., in order to populate that stress strain matrix, which is the either the stiffness matrix or the flexibility matrix. Usually it's the flexibility matrix, because those experiments are a little easier to perform, because to populate the flexibility matrix or the compliance matrix, in other words, you need to apply one stress at a time and keep all the other stresses equal to zero, which is much easier to do than to populate the stress, the stiffness matrix directly. What you have to do is to apply one strain at a time and keep all the other strains equal to zero. So for example, in this, if this were a specimen, then I want to apply only a strain along the length of this particular quantity, this particular rod. Then what I'm actually doing over here is that I have to ensure that the strains in the other direction are zero. So in other words, I should not allow for a change in the diameter of this particular rod. So that is much more difficult to do compared to dealing with applying only stress or load in one direction and keeping the loads zero in the other direction, which just means that I have to keep these phases without any contact with anything else, so that there is no equilibration of the stresses happening because of that contact. So that's all that I need to achieve. So that way the flexibility or compliance matrix is much easier to populate in an experiment. But the more important point is that the constitutive law is usually determined through such experiments. There are of course alternatives through procedures such as molecular dynamics, etc., where you try to understand from the atomic or molecular level and build up the constitutive law from that. So there are some theoretical formulations based on the atomic, interatomic forces or the intermolecular forces, especially in polymers, where you have a long chain of polymers. So in fact, you can explain elasticity itself from these concepts, why elasticity is happening at a macroscopic or a continuum level from what is happening at the micromechanical level, in terms of the long polymer chains getting unwound and then getting wound back, and therefore when you are stretching or leaving it free, it comes back to its original shape, because those polymer chains which uncoil themselves are then again recoiling back to their original position. That's how the polymer behaves. On the other hand, crystalline materials like metals, for example, there you are having these changes which are happening because of the interatomic forces. Those which are those atoms which are pulled apart from each other want to go back towards each other. So there are potentials which are associated, which are the interatomic potentials, etc., based on which you can arrive at the constitutive law as well. So that's an alternate way of approaching this whole problem. And there are also these phenomenological models where you are trying to understand from the various phenomena that are happening at the microscopic or even the mesoscopic level, somewhere between the microscopic and macroscopic, in order to understand the material behavior, introduce what are known as cohesive zones in a finite element kind of an analysis, and bring in properties of that cohesive zone, and eventually try to arrive at the overall structural behavior for the material in terms of what is known as the constitutive law. So that kind of summarizes this whole process. So this is a very, very important conceptual thing. As I said, everything else in this course will be as examples of this. So if there are any questions related to this, I'd be happy to clear that right now. Okay, I guess things are clear. So let me move on. Okay, now let's look at some specific examples of what we have talked about. Now we are dealing with axial bars and columns, and the reason why I've chosen these examples are the end results of these are already very familiar to most of you, and for those of you it's not yet familiar, it's very easy to catch up because the mathematics involved is very, very simple, and you can go through your textbook in order to understand how these equations are derived. But the axial bar or column, why is it important in a flight vehicle? There are examples of that. Any long structure to which there is a tension or a compression that is applied, like the stringers in a wing. You might recollect that a semi-monocoque construction has a wing skin, and then on the wing skin you have these along the span you have these stiffening members, long stiffening members, which are the stringers, as we talked about earlier. They are present in the fuselage as well, and the tail, so that we can have a reasonably thin skin. Otherwise the thickness of the skin would be much larger, what we call as a monocoque construction. So we've gone through all of that in one of the earliest classes of this course. So now those stringers are now like axial bars. Of course, in reality they are actually attached to the skin, and therefore they are taking the loads which are coming from the skin as well. But if you can just look at them as predominantly bending members, what is actually happening is that the top skin is undergoing, because of the lift distribution, the top skin is undergoing compression and is transferring that compression to the rods which are attached to the upper surface of the fuselage of the wing, and the bottom surface of the wing is something to which you have the stringers which are subjected to tension. So if you look at both of these sets of stringers, they are predominantly under tension, either tension for the bottom stringers and compression for the top stringers. But this reverses when the aircraft is on the ground and the only load is the self weight of the wing, and therefore the top is under tension and the bottom is under compression. But that's not very critical because the wing weight is much smaller compared to the overall aircraft weight, which is what has to be balanced by the lift. And in the performance of certain maneuvers, etc., there can be a load factor which is greater than 1 for almost all the aircraft, and therefore that becomes a more critical situation to deal with. So the top stringers would predominantly be designed for compression, and the bottom stringers would be predominantly designed for tension. So this being the case, either case, it is an axial load that you're basically introducing. So now we wanted to understand this from the perspective of this overall classification that we have done of the 4 sets of variables and the 3 sets of equations which relate them. So let's see how this happens. So in the let's look at this picture that you have over here. So you can see the red laser pointer, I hope. Can you?
Yes, sir.
Yeah. Okay.
Yes, so we can see.
Okay. So in this picture that I am showing over here, let's say we have a constant cross section rod that we have, which could be either subject.
I couldn't hear what you said.
Yeah, so we have a constant cross-section rod that we see over here, and we could apply either a tension as we have shown in this picture, or we could apply a compression. So let's take the example of tension to start with. So we are applying an outward force on these two ends, which is what we are calling as F1. The one subscript referring to the fact that this is along the x1 direction, which is along the length of this axial rod. So if that is the situation, and let's say because it's a constant cross section, the area of the cross section will denote by A. So this is the x1 coordinate. At one end it is x1 equal to 0, and the other end x1 equal to L being the length of the rod or bar or column that we have taken into account. It would be called a column if the direction of F1 was reversed, that it became a compressive load. So now this is the axial load case. So now if you look at the variable that we are having, the first variable, that is the load that we are talking about, is F1 in this particular case. So what is the main stress that comes out because of that is obviously the stress along the x1 direction, which is a normal stress, which is sigma 11. So the stress that we are interested in is the axial stress. First of all, let's identify all the variables that are involved. The load is F1. The stress is sigma 11, which is an axial stress. Now the corresponding strain that is there is the axial strain, which is epsilon 11. And finally, you have the deformation that you are interested in predominantly is the axial displacement U1. But that doesn't mean U1 is the only displacement which is happening. There is a Poisson's ratio which is non-zero. Poisson's ratio being non-zero means that there is going to be the other normal strains as well, epsilon 22 and epsilon 33, even in an isotropic material, and that is going to result in your U2 and U3 being non-zero as well. But right now, let's look at the dominant kind of deformations, the dominant stress, dominant strain, etc. So we are just trying to understand this overall broad picture that we are having, load, stress, strain and deformation, and the relationships between them. So it's very clear, load is F1, stress is sigma 11, strain is epsilon 11, and deformation is U1. Now what is the relationship between them? So let's start with the green quantity over here, which is the equilibrium equation that we are talking about. So the equilibrium equation, as we said, is basically a natural law. What is this natural law that is over here? Is that there has to be an equilibration of the forces. So in other words, Newton's third law is coming into picture. Every action has an equal and opposite reaction. So the action is the force that you're applying, which is F1, which is the load, and the reaction is basically what the material is offering towards that, which is the stress, and which is sigma 11. So obviously this F1 and sigma 11 cannot be independent of each other. They're related to each other, and that relationship is what we call as the equilibrium equation in this case. And it is quite straightforward and simple to see that using the St. Venant's principle, that is far away from the boundaries where this load is actually applied, there's going to be a uniform distribution of the stress in any cross section, and that stress is going to be given by F1 by A, or in other words, your F1 is equal to A times sigma 11. So that is basically your equilibrium equation in this case. Very straightforward and simple. It might look very trivial to you that I'm spending so much time on this, but it's essential, because if you understand this, understanding anything else in structural mechanics becomes very simple if you put these in perspective. Instead of just looking at this as a separate individual topic or a problem, if you look at it, how it fits into this overall picture that we are drawing over here, then you would see that everything else will also fall into the similar kind of a systematic structure or logic. So that's the reason why I'm emphasizing and spending a little more time on this, though it might be a little painful for some of you who are familiar with these things. So bear with me. The next thing is, we want to relate the stress to the strain. The stress, as we said, the dominant stress is sigma 11 and the dominant strain is epsilon 11. Basically both are normal stresses and normal strains in the axial direction, what we call as the axial normal stress and axial normal strain, and that's why we are denoting it by sigma 11 and epsilon 11, having introduced the x1 coordinate system in this way. Now if you look at an experiment which is to be performed in order to determine the relationship between them, all that you have to do is apply only sigma 11, keep the other stresses to be zero. In the case of an isotropic material, which is what we'll deal with to start with, there is no coupling between the shear stresses and the normal strains. Therefore, even if the shear stresses are applied, it's not going to matter. But what does need to be specified here, very importantly, is that sigma 22 and sigma 33 have to be kept zero. If sigma 22 and sigma 33 are not kept zero, then this equation that we have, the constitutive law saying that epsilon 11 is sigma 11 by E, is not valid, because you would have additional terms on the left hand side related to sigma 22 and sigma 33 which are going to be multiplied by a nu by E factor, which are going to contribute towards the epsilon 11 as well. So that's very important to understand, that we need to specify this, and if it's a composite material or any other anisotropic material in general, we not only need to specify sigma 22 and sigma 33 equal to 0, we need to specify that all the three shear stresses, sigma 1 2, sigma 2 3 and sigma 3 1 are also equal to 0. Only non-zero stress that we are applying, or actually we are applying the load which is exhibiting itself in the form of a stress, the only non-zero stress that is there is sigma 1 1. So in such a situation, there is a very simple relationship based on the Hooke's law that we have, which is sigma 1 1 is equal to E times epsilon 1 1, which is what is written over here. Next, let's go to the relationship between the strain and the deformation, which we said is kinematics, which should depend only on the geometry. So now, as you see, constitutive law depends only on the material, because the relationship between your sigma 1 1 and epsilon 1 1 is a proportional relationship, and the constant of proportionality is 1 by E, and E is 1 E or 1 by E are functions only of the material which is used, which is what we said over there. On the other hand, the equilibrium equation that we have over here is bringing in a cross-sectional area A, but that is because we are interested in the load which is applied over an entire area, and then it is getting distributed at all points of a given cross-section. Therefore, that A is coming. A is a geometric parameter, but in that sense it is not kinematics, because it's only kinematics which depends on the geometry. But here the reason why this A is coming is that each one of those elements, small elements, infinitesimal elements in the cross section, infinitesimal area elements, are offering a resistance to the load that you're applying, and you're basically integrating over all that, and that's where that particular area is coming from. Now let's go back and look at the relationship between the strain and the deformation over here, which is the kinematics. And if we look at, for simplicity, just like here for the for the simplicity, we had taken here only isotropic material. Here also we will take a linear strain displacement relationship, which is actually not valid enough for the examples that we are talking about in stringers and wings, fuselage and tails, can go through very large deformations, very large displacements, and therefore you might have to bring in the non-linear terms as well. But to start with, let's say we take the simple linear relationship between the axial strain and the deformation, which is your axial displacement U1. Now that's a simple differential equation, epsilon 1 1 equal to dou U1 by dou X1. In fact, in this particular problem, U1 depends only on X1, and if F1 is not a dynamic load, U1 doesn't depend even on time or the other two spatial coordinates X2 and X3, which means that I could even put this as du1 by dx1, that is a ordinary derivative instead of a partial derivative. But since we are going to extend this whole thing to other coupled problems later on, let's keep the partial derivative over here, but knowing that it's actually an ordinary derivative, that is all that is necessary over here. So epsilon 1 1 is equal to dou u1 by dou x1 becomes the kinematic equation of concern over here. So now let's look at what's happening overall. So now if we substitute this epsilon, if we substitute this epsilon 1 1 expression that from the kinematics into the constitutive law, and then take the sigma 1 1 and substitute into the equilibrium equation, we end up with what we are interested in, which is basically the relation between the cos, which is the load, and the effect, which is the deformation. So this stress and strain were artificial quantities that we introduced in between in order to enable the step-by-step approach. And you see that each one of these equations, three equations, F1 equal to A sigma 1 1, 1 by E sigma 1 1 equal to epsilon 1 1, and epsilon 1 1 equal to dou u1 by dou x1 are very straightforward and simple equations. But now we want the relationship not between these strange quantities called stresses and strains that we have introduced in between, but the actual observable quantities, which are the deformation and the loads. And we want to do that. We want to eliminate, using these three equations that we developed, we want to eliminate the strain and the stress, that is sigma 1 1 and epsilon 1 1. When we do that, we end up with this particular equation that you're very familiar with. F1 is equal to EA into dou U1 by dou X1. So now if you actually look at this, what is actually happening over here is that you are relating your F1 to U1, but not U1 itself, but to its derivative, that is du1 by dx1, and that derivative is related to F1 through a constant of proportionality, which is EA. But the more important point to observe over here is that your E is a material property, whereas A is a geometric property, and so that relationship between the cos, which is the load F1, and the effect, which is your dou U1 by dou X1, is basically a combination of the material property, which is Young's modulus, and the geometric property, which is the cross-sectional area. Now this is a standard result that you will observe everywhere else. We will look through two more examples in today's class, hopefully at least one more example, and then we will see that a very similar structure is developing in all kinds of problems. To start with, we are looking at decoupled problems. Once we go look at coupled problems, instead of having a single scalar proportionality factor here, we will end up with a matrix, and instead of a single load over here, we will have a vector of loads or a column matrix of loads. Similarly here, instead of a single displacement field based variable or its derivative, we would have a column of those. So that's basically what we eventually want to get to. But the relationship between those two would become a matrix of constants, and that matrix will involve a combination of material properties and geometric properties. So it is this combination that is very, very important. So though here in this case it appears that the A came from the equilibrium equation, in reality it's a contribution of the kinematics, because the area is something which is making up those points, at each one of which there is the stress and the strain. So it may not be very clear in this simplistic example that the area is actually coming from the kinematics, but it's coming from the equilibrium equations. But the effect is that the constitutive law, depending on the material, and the kinematics depending on the geometry, is what eventually brings a dependence of this cause-effect relationship on both the material property as well as the geometry. So as I explained over here, it's basically what is the actual natural law is at a point what is actually happening in terms of how an action is equal and opposite to a reaction. But when we are integrating over that geometric area is when we end up with this kind of an equilibrium equation over here, and that's why this is contributing the A. But whatever that might be, this equilibrium per se, or let's say the law of conservation of translational momentum from which this is actually derived, is not a geometric feature. It is actually a purely a natural law. Just that because we are integrating that over the entire cross section, that the cross sectional area comes into picture. But the end effect is that the relationship between the cause and the effect will depend always on two sets of parameters. One will be material properties, the other will be geometric properties. In this simple example, it just became a product of those two. In many other simple examples also, we will see it just becomes a product of these two. But there could be more complicated examples where a more intricate relationship will be required. But whatever it is, you are basically having a relationship between these two. And the other thing is, here we took let's say linear constitutive law, because we have assumed material linearity, and we have also assumed a linear strain displacement relationship, in other words geometric nonlinearity. So material linearity and geometric linearity has led this to be a linear equation between the cos, which is F1, and the effect, which is U1. So a linear ordinary differential equation is what you end up with, which you can easily integrate to get U1 in terms of F1 by applying the appropriate boundary conditions at the two ends, and then solving for U1 as a function of F1. So in this case, F1 was just a tip load. It could be a distributed load along the length, as is the case with a stringer, for example, in the wing. So then you would have a little more complication in terms of the integration once you bring in the fact that the displacements are large, and therefore additional terms have to be taken into account in the strain. There might be a coupling and you might have the other loads coming into picture. So you have to solve a couple problems. So things will be a little more messy, but nonetheless the flavor remains the same. There is a relationship between the cause and the effect, and that relationship is supported by the material and the geometric properties that are involved over here. So now if you look at which geometric property specifically is involved in this example, it is the cross-sectional area. So the area is not going to depend on the shape. It's only on how much of material is within that particular cross-sectional area. So if I have a rectangular or square cross-section like this, or I have a circular cross-section like this, or if I have an I section like this, in all these three cases, you're going to end up, as long as the cross-sectional area itself A remains the same, you're going to have the same end result in terms of how U1 is going to behave with F1. It's not going to change at all. So that's what the assumptions or simplicity of this particular equation leads us to believe. But if you reverse the F1, then as you increase the F1, the behavior after a certain value of F1 will depend upon the shape as well, not only the size, not only the cross-sectional area. Why? Because if it is there's no preferred shape in designing a material, designing a rod, if you know that it's only going to be subjected to tension or very less amount of compression. On the other hand, if we know that a rod is predominantly going to be under compression, that is, if F1 is going to be negative, then you know that there is a possibility, as F1 becomes large in magnitude, that there can be an elastic instability or buckling. And therefore, in such situation, not only the cross-sectional area value, but also the way you design that shape will also matter. Which is why, for example, the top stringers of a fuselage, the geometry is very cross-sectional geometry is very important, because we know that there is a lift distribution which is bending the wing in this way, and because it's bending the wing in this way, the top stringers are under compression, and therefore if the lift reaches a very large value during a maneuver, for example, of the aircraft, it is possible that the stringer might reach a load very close to its buckling load. If the skin buckles, that is well and good, that's okay, because the stringer can still take the load. If the skin has buckled and later this stringer also buckles, then we have a major issue. So we need to avoid that. So we will design the shape, the cross-sectional shape of that stringer to be such that it will maximize the buckling load, or in other words, it will delay the buckling from happening to a much larger tensile compressive load that this stringer is taking. So how do you go about that? So there are many ways to do that. So buckling strength can be increased in at least three major ways. One is by introducing your transverse support. So in the case of the wing, you're having these ribs. So you will introduce ribs at a closer, in other words, the pitch you are reducing. So the distance between two ribs is going to be lesser. So in other words, you are reducing the effective length of the column, which is your stringer. So the same thing what I'm talking about applies for the spar caps as well, the spar flanges. But the basic idea is that you are reducing the effective length of each one of those compressive members so that the buckling is delayed. So you are familiar with the Euler buckling formula, that there's a dependence on inverse dependence on L squared, and therefore reducing L can tremendously increase the buckling load. So that's one standard way of delaying buckling or avoiding buckling altogether, is by having transverse supports closer to each other, so they will shorten the buckle length. So in the case of wings, of course, it's the ribs. In the case of the fuselage, it's what we introduced earlier using various schematics as the frames or bulkheads that are there. In the case of the tail also, if it's a large aircraft, having a fairly large vertical or horizontal tail, then you would have ribs in the horizontal and vertical tails as well. The second way is depending upon which kind of buckling might occur. So in other words, what is the susceptibility when there is a compressive load on this member? What is its predominant susceptibility? Is it going to bend, or is it going to, because of the compressive load, it is going to twist? So that depends upon which of these are dominating. That is, if the bending stiffness is very low in a particular direction, it might be high in another direction. But if it is low in one direction, the susceptibility because of the compression will be more towards what is known as a flexural buckling. So in other words, it bends this way when the compressive load goes beyond a certain point. On the other hand, if the torsional stiffness is very, very low and the bending stiffness is reasonably high, then what will happen is, as I increase my compressive load, it would just twist. So the instability is exhibited in the form of a large twist angle that results because of the compressive load, and that is a torsional buckling that is basically happening. So how do we go about avoiding these two? We have to identify what is the bending stiffness, find it if it is low, increase it. Let's say by going for an I section instead of a rectangular or circular cross section for the stringer. Similarly, if it's if the torsional stiffness is very low and it's susceptible to torsional buckling, I might go for a closed section, let's say a hollow closed section like a tubular kind of a stringer, which is very rare because rarely torsional buckling would occur in this case of a stringer. So, but if it was a particular design situation, then how you would avoid that torsional buckling is by going for a closed section instead of an open section like an I section, etc. So these are the things that you need to kind of remember. So let's see. Okay, I think I can go with probably another example. Okay, let's take the example of a torsional member now. Once again, I want to bring it into this bigger perspective. That's the whole purpose of this exercise, because I am again of the know that many of you are familiar with this particular problem. So that's the reason why I've chosen it. In fact, knowing fully well that you know it, so that you see where this overall picture emerges. So examples where you can have torsional members in an aircraft are the drive shafts that you can have. You could have the wing box, which is basically again something that we illustrated for actual aircraft. Many examples we have already talked about, showing pictures. There is others that you can see in your textbook or the other reference books. So what this wing box is basically is that you have in the wing you would have the front spar and the rear spar, and between these front spar and rear spar you have the top skin and the bottom skin, and the front spar's web and the rear spar's web along with this top skin and the bottom skin basically form a box. Idealized to be rectangular, but actually there is a curved member on the top and the bottom. The spar webs are of course usually straight, that's not an issue, but these are slightly curved, as you know, conforming to the airfoil shape that we want to have. Usually the bottom one is almost flat, but the top one has a curvature that you can't ignore. But nonetheless, it's basically a box, or in other words, a closed cross section that you have, which is really suitable for taking torsional loads. Where are these torsional loads coming from? The torsional load is actually coming from the aerodynamics and or the control surfaces and or the engine that you are having being slightly displaced from the center of twist or the shear center of the airfoil cross section, and therefore because of that you would have a certain moment that is there. From the aerodynamics, how does it come? There is a pitching moment that is there, and depending on, so if you take the loads to act at the aerodynamic center, that is the lift and the drag, there is also a pitching moment that is there, which changes with the depending upon the location, and therefore since we are interested in about the center of twist or the shear center, there is going to be a moment there. So that is basically a torque. You can think of a cantilever shaft which is having a torque not just at the tip but throughout the length which is distributed. But now let's take a simpler example of that situation, very similar to what we looked at in the previous example. So now we are going to look at the load as a torque. So
Sorry, I couldn't hear.
so the torque is basically T, which in our notation is M1 because it's a moment, therefore M, and it's parallel to the x1 direction, so we call it M1. So that moment M1 is given by the torque that you're applying at the two ends. So let's say it's not a distributed torque, but you're applying on the shaft torque at its two ends, which is T at this end and T at the other end, so that it is under static equilibrium. And now we want to see what happens at a particular cross section, which is somewhere in between, so which is at a value of x1, x1 taking the range from 0 all the way up to L. Now, what is the cross section? The cross section we will take again for simplicity. As you know, the simplest situation is where you have circular cross section. So, but we will bring it a little more realistic towards at least let's say a shaft, if not a wing box. So we will make it a thin-walled hollow circular shaft. So therefore the radius is going to vary from Ri, which is the internal radius, that is of the inner surface of that shaft, to the Ro, which is the outer radius or outer surface of the shaft. So now let's look at from the bigger picture perspective. So the load that we are going to talk about over here is basically your T. The stress that is going to result because of that is predominantly a shear stress tau. Which particular shear stress? It's going to be on the cross section, to which the normal is the x1 direction and therefore the b1 vector. So the first subscript for the shear stress should be 1, and it is a stress because of the torque, and therefore it is going to be circular. And so if you introduce a polar coordinate system, the shear stress itself is going to be in the theta direction. So it's on the one face, that is a face to which the x1 direction is normal, and the direction of the load itself is along the theta direction, so it's a tau 1 theta. So that's what is illustrated over here. It is tau 1 theta. So that's the shear stress. Correspondingly, you have a shear strain, which is also gamma 1 theta, the corresponding shear strain that is there, that is the strain. And then we come to the deformation finally. In the previous example, it was an extension u1 as a function of x1. Now it's a twist angle, we will call as, let's say, phi, which is going to be a function of x1. So instead of u1 being a function of x1 in the rod problem, in the shaft problem we have a twist angle phi1, which is a function of x1. So now we want to relate these quantities. Let's go from the right end this time. We want to relate the deformation, which is phi1, to the strain, which is gamma 1 theta. That is going to be given by this relationship for this simple example of a circular shaft. The gamma 1 theta is going to be just the corresponding radial location of that material point at which you are interested in the strain. So this R is varying in this range from Ri to R0. So that R multiplied by the rate of change of that twist per unit length, that is dou phi1 by dou x1. So this is a purely geometrical exercise. Your textbook has that. You can go through that derivation if some of you have not been exposed to it, but those of you who have been exposed to it and have forgotten can also review or revise that to see this. But this is a fairly straightforward and simple thing to see, that there is a rotation which is happening phi. That phi, how it is changing along the x1 direction, multiplied by the radius, is going to give you a change in the right angle that is going to happen, because the same strain gamma 1 theta is also going to be appearing complementarily as gamma theta 1, that is on the theta face, that is on a circumferential face in the one direction. So that is along the length of the shaft, but on a circumferential face. is the same as what is happening on the cross section in the circumferential direction. So these are complementary strains, gamma 1 theta and gamma theta 1. So if you derive an expression for one, you derive the expression for the other. So it's very easy to derive the expression for gamma theta 1 and see that it is basically equal to how phi1 is varying along the length of the shaft, and therefore how that is getting multiplied by the radius in order to determine the change in the angle, because we're talking of small angles over here. Therefore it is just given by r times dou phi1 by dou x1. So that is coming purely from the geometry over there. Now coming to the constitutive law, where we want to relate gamma 1 theta to tau 1 theta. Again, we are going to talk about isotropic shaft or an isotropic wing box, let's say circular, which is very rare. But if that is the case, then you would have once again a linear relationship between the shear stress and the shear strain, and the constant of proportionality this time is going to be given by 1 by g. And here for an isotropic material, we do not need to specify that the other stresses are equal to 0, because anyway there is no coupling between any shear stress and the other shear strains, or between the shear stress and any of the normal strains. So therefore the shear strain gamma 1 theta is going to depend only on tau 1 theta, and it's going to depend linearly. Again, this relationship can also be nonlinear when there are large deformations, in which case the large rotation per unit length is what we are talking about. So when that is there, this relationship can become nonlinear as well. So we are assuming that the rotations are small, and we are assuming the strain is small, and therefore if rotation is small, this is linear, the kinematic equation. If the strain is small, the constitutive law is linear. And then finally we come to the equilibrium equation, which is very similar to in a bending moment problem, you know, my by I is the sigma. See here you have tau is equal to torque into the radius divided by j, which is the torsional rigidity that is basically involved. But in the case of a circular cross section, whether it is solid or hollow, you know that that is happens to be identical to the polar moment of inertia. Now this is something that you need to be very familiar with, because most of you are exposed only to circular shafts. So you tend to think that J is always the polar moment of inertia. No, it's only for the case of the circular cross section that it is equal to the polar moment of inertia. For all other cases, there is a certain way of determining it, and you can go through your textbook to see for various cases how that J is actually determined, because you will need that for the homework that I'm going to give. So that's why I'm stressing on that. But now, if you look at it more from a specific notational point of view, the tau is actually tau 1 theta, and the torque that you're talking about is an m1, and the radius that you're having is r, and of course j is over there. So now this is the relationship which is basically coming from equilibrium. Once again, what is happening is you're applying a certain action which is in the form of a torque, and the material of the shaft is reacting to it by means of a stress. So that stress is related to that torque through this particular relationship of R by J being the proportionality factor over here. Very similar to the proportionality factor being A, cross-sectional area, in the case of, or 1 by A in the previous problem of the rod. So this three are once again combined. So in other words, we substitute for the shear strain into the constitutive law, and then the constitutive law gives therefore the shear stress in terms of phi1, and then we come and substitute this over here. So once again here I've written partial derivative of phi1 with respect to x1, but in reality in this simple problem it's actually an ordinary derivative of d phi1 by dx1, but keeping it general for the future. So now once we substitute the kinematic equation into the constitutive and constitutive into the equilibrium equation, we end up with this equation, which in the form looks very similar to the equation we had in the previous example of a rod. Remember that what we had there was that F1, or the axial load, is given by EA times the dou U1 by dou X1. Here instead of U1 we have phi1, that is instead of an axial displacement we have a rotation which is of the cross section about a normal which is perpendicular, about a line which is perpendicular to that, which is basically your x1 direction. That's why we call it phi1 as opposed to phi2 or phi3, which are rotations in the about the x2 or x3 directions. So now that is basically related to t. So in other words, the cos is the load, which is the torque that you're applying at the two ends, and the end result is a deformation, which is the twist angle phi1, and those two are related by a linear ordinary differential equation, and that coefficient being constant, a constant coefficient ordinary differential equation, and that constant coefficient once again is made out of two parts. So this is what I want to emphasize and you to notice very clearly, so that you understand more complicated problems from this simple perspective. That it involves a material property, which is the shear modulus or shear modulus of rigidity, which is G, or sometimes referred to by the notation mu, if you use Lamé parameters of lambda and mu. And then your J, which is a geometric property, what we call as the torsional constant, which in this simple case happens to be just the polar moment of inertia IP, which is given by 1/2 pi of R0 power 4 minus Ri power 4, which can be replaced using the a squared minus b squared formula as a plus b into a minus b. Here a is R0 squared and b is Ri squared, and therefore we can replace it as R0 squared plus Ri squared into R0 squared minus Ri squared, and that can in turn again be factored again as R0 plus Ri into R0 minus Ri, and we can replace R0 minus Ri as the thickness T of this shell that we have over here, that is basically R0 minus Ri, and then we can replace R0 plus Ri as twice the average radius, and because the thickness is very small compared to the either Ri or R0, we can replace this also as R bar squared twice. So once we do that, we end up with the polar moment of inertia approximately for a thin walled circular shaft to be 2 pi t times r bar cube, where r bar is the average radius. Now what is important is to see that pi r bar squared would be the area enclosed by that closed cross section, and therefore if you write it in terms of that, your Gj, or rather J, is proportional to your a bar power 3 by 2, and this is something to remember because you would see some kind of a similar kind of a behavior even for non-circular cross sections, even though their polar moment of inertia is not involved, but a torsional constant is involved, and the way to determine it, formula for which you can extract from your textbook for various types of cross sections. Now let's go to this. So now one of the inferences that you have from this one, of course, is that it depends on a material property and a geometric property, that is G and J coming together. Other fact is that J is going to be proportional to a power 3 by 2. So in other words, larger the a bar, it's going to be higher. Now this a bar is different from a that we talked about in the previous example, which was the cross-sectional area. Now we are talking about the area which is enclosed by the mid surface of this shaft. So that is the area a bar that we are talking about over here. So the same cross-sectional area can be redistributed in such a way that you have a larger a bar. How do you do that? Moving away from having a solid shaft to a smaller and smaller thickness thin walled shaft that is of much larger average radius. So you move the material farther and farther away, use the same amount of material, so in other words the same length of the shaft, same cross-sectional area, but that cross-sectional area starting with a solid small diameter is becoming larger and larger diameter, but of thinner and thinner hollow tubes. So that tubular geometry that you're going to have, so which basically means that you can have a larger J and therefore a larger Gj, and therefore for any given torque you can have a smaller dou phi1 by dou x1. In other words, the amount of twist rate is going to be smaller, and therefore its deformation is going to be smaller. Essentially you can also show that the shear stress is going to be affected by this behavior, and you can delay your failure of the structural material as well. So in this simple case, if you move from a thin-walled, large diameter hollow shaft to a thick-walled, small diameter shaft, you're going to drastically reduce GJ, and therefore drastically increase your twist rate, and therefore the possibilities of failure as well. So now that because remember that twist rate is directly related to the shear strain, and if you know what shear strain it failed, that particular material fails, you know that will be reached very quickly. So now very similar, of course, at the other end of the spectrum are the solid shafts of the same material and mass. So now, just to give a comparison, an example from your textbook is GJ for a 1 millimeter thick 100 mm diameter shaft, or 50 mm radius, that is 100 mm diameter shaft, but 1 mm thickness, would have the same cross sectional area as a 20 millimeters solid shaft. But if you calculate GJ using this formula of 2 pi t r bar cube, you will see that the GJ for the thin-walled shaft is 50 times the GJ or torsional stiffness for the solid shaft. So in other words, you are keeping the same amount of material, that is the mass, the cross-sectional area is the same, but just by redistributing it farther away from the center of that cross-section, you are able to increase by as much as 50 times without adding any new material, just by changing the geometry. So the amount of change that you can see. Similarly, if you go for a material with a larger G, you can again increase GJ, but you can't have such a large increase. So geometry changes play a much more critical role in flight vehicle structure design than just changing the material alone. Yes, we are going from a metal to a composite for its better superior properties, as we have already discussed, but once we do that, still there is a lot more room to improve the structure by changing the geometry accordingly, which is so in this case you see that even though A1 is equal to A2, that is the cross-sectional areas for these two cases, solid shaft and hollow shaft, are the same, just by moving it away from the center, we are increasing the torsional stiffness by as much as 50 times. So the homework that you have is on a similar line, just like the circular shaft. So you can't use this formula anymore, which is valid only for the circular shaft. Check out what you need to do for the actual kind of spar web skin kind of a combination, which results in a wing box, which is actually not a rectangular box, but for your case, let's assume it's a thin-walled rectangular box beam, so that the cover skin makes 90 degree with the spar, front spar, and similarly the cover skin makes 90 degree with the rear spar as well, similarly with the bottom skin as well. So it's basically a rectangular cross section, and the thickness is very small compared to the two dimensions, let's say A by B. Let's say the height is A and the width or breadth is B. So this A and B are much larger compared to the thickness, and assume for this simple example that the thickness of the cover skin, both on the top and the bottom, as well as the spar webs, are all of the same thickness, which may not be the case in reality for actual spar wing box. You might have different thicknesses, you might even have different materials, and the way these are joined also, the joint will matter, the flexibility of that joint, and therefore the change in angle of that joint will matter. For your simple example, you will assume that joint is rigid so that the 90 degree is maintained. It's only the entire rectangular cross section which rotates from with respect to the fixed end of the wing. The tip is rotating by a certain amount, and therefore the total rotation at the tip divided by the half the wingspan gives you the dou phi1 by dou x1 in that particular case. Now, all of that is not significant, but I'm just putting it in perspective in terms of the actual flight vehicle structure problem, how it relates to. But the homework is to calculate this GJ. Of course, you're having the same material in both cases, so the G doesn't matter actually. It's only the ratio of J which matters, but to identify the right kind of formula by going through your reference books, what is the J for a rectangular cross section, which is not solid rectangular cross section but a thin walled rectangular cross section, and how that J can differ by going from a solid rectangular cross section shaft to one which is a kind of a box beam of the same cross sectional area. In other words, you have 4 elements to it, 2 which are of the length A, so 2A, and 2 which are of the length B, which are 2B, all of the same thickness, so 2 into A plus B whole multiplied by T, which is the thickness, is the cross sectional area. So for both of these problems, the solid shaft as well as the box beam, you are going to have the same cross sectional area, 2 into A plus B times T. So that A1 B1 is going to be, for the solid shaft, is going to be given by 2 into A plus B times T for the thin walled shaft. So in such a situation, I want you to compare and come up with this kind of a factor that we talked about. In the case of a circular shaft, we said it's 50 times by changing from this to this. How it will change as a function of that thickness ratio, that is T to T by A or T by B ratio, how it's going to depend on that. The smaller that becomes, the larger this difference or factor of Gj is going to be in these two cases, that is between the rectangular box beam and the rectangular solid shaft. So with this I conclude today's class. So remember and revise this bigger picture, because we will go through probably 1 or 2 more examples, simplistic examples, and then go on with the rest of the course, and every time we will try to revisit this whole thing to see where each one of those individual derivations fit into the bigger picture. So thank you very much. So the class is over, but if any of you have any questions, because I've taken a lot more time, so if any of you have any questions, you can stay back and ask me. I'll be happy to answer.
Hello, sir.
Yes, Samanlal, go ahead.
Sir, is this torsional equations valid for this square or rectangular cross section? Because whatever I know is this is only valid for circular cross section.
No, the expression for J is valid only for a circular cross section, but this T is equal to Gj by dou phi1 by dou x1 is valid generally for any cross section. So the way you define J will change depending on the cross sectional geometry, but this whole expression will not change as long as you are still having a small deformation, which is the only case under which this equation is valid, the kinematic equation, and small strain, which is the only case under which this is valid for isotropic materials, so that there is no coupling with the other stresses. So as long as these assumptions of isotropy, material linearity and geometric linearity remain, so this expression remains the same. It's only the way J is defined which is going to be different.
Okay, thank you, sir.
Yeah. But what you're saying to some extent is true, Samanvai, because in the case of the thin-walled cross sections, what is going to happen, which is in fact will fail even in the case of the thin-walled circular cross sections, is that this is no longer actually holding good. Okay, so but what we are primarily interested in is comparing the torsional stiffness, for which irrespective of how this geometric nonlinearity is built up, only this expression is going to change. The multiplying factor is not going to change. So that multiplying factor is going to primarily come from your equilibrium equation, which is going to remain similar, and your constitutive law. So therefore it's not going to change unless you change the material. So even in such a situation, all that we are comparing is the J for the different geometries, and we are just coming to the conclusion that thin-walled cross sections, irrespective of whether it is circular or rectangular, are going to be better for this application compared to any solid cross section or a thick-walled cross section of the same cross-sectional area.
Thank you, sir. We'll do that, sir.
Sure.
Okay, thank you.
Okay, anybody else? Any questions? Okay, thank you very much then. We'll meet next Tuesday. See you. Bye-bye.
मृत्युञ्जय मन्त्राः त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा